This is not a good day for my network. Okay. Let's hope it works now. All right. So in the previous lecture, we started looking at potential energy, bungee jumping, and we started discussing about potential energy and the change in potential energies. Okay. We looked at the change in potential energy, and we showed that it is, independent of the path taken. And we reached here. We said that if the work done by a force in a system is independent of the path taken, then the force is called a conservative force. So we can go left, we can go right, we can take as convoluted, long or short a path we want. The change in the potential energy or the amount of work that is done is still the same. Okay. It's like me saying that you want to, no, I'm not giving you money, I'm taking money. I want to get 100 riyals. Okay. Now, whether you give it to me in 1 riyal notes or you give it to me in 50 riyal notes, في نهاية المطاف, am I talking to myself? Can you hear me? Okay.
واضح دكتور.
Okay. So في نهاية المطاف, I will get 100 riyals. Whether it's in 250 riyal notes or in 101 riyal notes. Okay. It doesn't matter. You give me 1 riyal every day, eventually I'll get 100. You give me 50 riyal notes for 2 days, خلصنا, I'll still get 100. And this is basically what a conservative force is. Okay. It also says that if I start and come back to go somewhere and come back to the same position, even if using a different route, my net change is going to be 0. So if you give me 100 riyals in 1 riyal notes, and then I give you 250 riyal notes, we have used 2 different ways. You used 1 riyal notes, I used 50 riyal notes, but في نهاية المطاف the effect was plus 100 minus 100. So the net was 0. Now, we'll start with a PIQ. I noticed that not many of you have filled the survey so far. Please fill it in. It's the only way we can improve this course further. Okay, education is an ongoing process, and unless we are able to unless we're able to improve our to get feedback, we cannot improve our basically our education services. So it takes 5 minutes, no more. Take your time, fill it in. Okay, so that, well, maybe for the rest of the course it can get better, or at least for your friends later on, it will get better. Okay. Okay, so I've enabled it on PIQ. It's in PIQ 1, section 8.1-8.2, the first one. Okay, and the question says, the figure shows 3 paths. The same force F does the indicated work on a particle moving along each of these paths in the indicated direction. Is this force conservative? Yes, no, yes, but with something, or yes, but with something else. So take a couple of minutes, try it out, and see what happens. I'll give you one more minute, and then we see what seems to be the consensus. Very few attempts so far. We'll wait another minute. Okay, 20 more seconds. Okay. All right. Let's see. So the majority of people said no, but the second highest was yes, but only for the path with minus 60 joules. So what you're basically saying is, as long as I go plus 60 and minus 60, then it's conservative. We will just not look at this for the time being. And that is not possible. Okay? A force is either conservative or non-conservative. To be a conservative force, okay, one, it needs to be path independent, and two, work going forwards is equal to minus work going backwards for all paths. Now, since here we seem to be having two paths going forward, 160, one minus 60, it's not path independent. It changes with the path. انتهينا. It's not a conservative force. Even worse, we have these two paths going forward and backwards, and both of them are 60 joules. So even number 2 is not correct, because going forward and backward is not the same value. Okay, is this bit clear?
Yes, Doctor.
Now, examples of conservative forces are gravitational forces, spring forces, okay, which are the two that we have done so far. There are other types of conservative forces, but you need to prove it mathematically. It's not enough to try 2, 3, 4, 5, 10 different paths, and if they give you the same result, okay, they are conservative. So what I can do is, I can see A and B, and I can do, okay, path A, path 2, path 3, path 4, path 5, and I can do like 10 paths, right? And see if they give me the same numbers. Then what I do is I go the opposite way. I go, opposite, 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 and so on and so forth, and see if they give me the same result or not. Okay. Now, although this might give me an indication, this is not enough proof to say whether something is conservative or not. We need to mathematically prove whether a force is conservative or not. Non-conservative forces are those for which going forward is not the same as coming backward. We said there are two rules. One, that it's path independent, and two, that going backward is opposite of going forward. Same number, different sign. Right? Okay. So if that is not true, if going forward is not the same as coming backward, then it's a non-conservative force. Can you think of a force which is non-conservative, which we have been dealing with so far?
Friction.
Okay, good. That's the most obvious example. That's an excellent example. Friction. In friction, we have kinetic energy of something moving, and by friction, it becomes heat. Now, this thermal energy is lost and gone. If I bring something in reverse, so if I take something, push it, by friction, it will stop. If I push it backwards, will I get that heat by friction back? I don't.
No.
Yeah. So for gravity, I go up, I get some potential energy, mgh. I go back down, I get it back. Right? But with friction, it doesn't work this way. If I lose my energy on the way up, I cannot just bring it back and say, okay, friction is giving me my energy back. That is gone. So it's not conservative, and thermal energy is not a potential energy. Now, there's something quite important here which we need to pay attention to. It says thermal energy is lost and cannot be put back into Ke of the object via the friction force. Why am I mentioning that it cannot be put back via the friction force? Because it is possible to put it back, maybe, via other forces. Yeah. Say, for example, I have a system, okay, whereby why, for example, I'll give you a real one. Tesla cars. Who here knows Tesla cars? Elon Musk, Tesla. Everyone here knows Elon Musk and Tesla? Good.
Yes.
Okay. Tesla cars are famous for something. When you brake, you don't lose all of your energy via friction. It actually collects that heat and puts it back into the battery. It's called regenerative braking. Okay. I drive a Toyota Camry, which is hybrid. It does the same thing. Okay. But here's the important point. Okay, we might be getting that energy back, but are we getting it back via the same force? We lost it by friction. Are we getting it back by friction? No. I might be getting it back, but it is using a different force not the same force. So we're not really conserving here. Yeah, we are just smart enough to be able to collect it. We're not. It's not a conservative force. Now, this is a nice sample problem. Okay, in your book, sample problem 8.01, which shows why conservative forces are really, really lovely. You have a 2 kilogram block of cheese. That is a big, big block of cheese. في واحد بيصير له غازات إذا أكلها كامل. So 2 kilogram block of cheese, which is very slippery, which means means no friction. It slides down this path from A to B. Now, if I go over this route, هذا الشارع, my total length is 2 meters. My vertical height is 0.80 meters. And I want to see how much work is done by gravity on cheese. Now, before we know about conservative and non-conservative forces, how would we do this calculation? How would we calculate the work done by gravity on cheese? We would use our equation, W equals F dot T. But since the distance here is not straight, فيها نزول وفيها صعود we would have to say work equals integral of fx dx from xi to xf plus fy dy from yi to yf. And I can see the horror in all of your eyes, even though you have not opened your webcams. I can see the horror in your eyes. Integration. Guess what? Nobody really likes integration. Not even people who do it for a living. It's a pain. So I have another way to do it. Since this is a conservative force, the path I take doesn't matter. So why do I take this weird ass path which, is painful and needs integration? I can simply take a straight line. But wait, why take a straight line and deal with sines and cosines? I don't like this. I am going to go on this path. I will imagine I have gone this path instead of this weird ass path. So let me see the work I am doing on this path. In the horizontal, my F dot T mg d cosine theta. What's the angle between the horizontal and the gravitational force? 90 degrees. So according to physics, we have not done any work. See, 0. Then I go vertical. Vertically, mgd cosine theta. Put in m, put in g, put in d, put in theta, and you end up with 15.7 joules. The sum of these two is just 15.7, approximately 16 joules. Simple multiplication. 2 multiplications, one of them simplifies to 0, no integration, no function, no nothing. So what do you think? Conservative forces, nice or not nice? Okay. So when we were describing, work F dot D, and cosine theta, we said it's like, when mom asks us to do work. Okay, it has to be done exactly that way or it doesn't count. Well, guess what? Conservative forces is when dad asks you to do something. It doesn't really matter how you do it. As long as you do what dad wanted, he's happy. Abdul Wadud. So in this case, your cosine is fixed at 0 and 90 degrees because we chose this path. Because we chose this path, our angle here is 0 and here is 90 degrees. Sorry, here is 90 degrees and here is 0. Yeah. So you need to look at the path that you have chosen. Now we've been talking about potential energies for a bit, but how do we determine the value of the potential energy? In the case of gravity, for example, we said if we go up, we're doing work, we're changing potential energy, right? We come down, we lose the potential energy, but we gain energy, we gain work. Correct? So work is F dot D, and the change in potential energy is minus the work. So if I give you 100 reals, the change in my bank balance is minus 100 reals. I really wish it wasn't, but apparently it is. Okay. Let's do this question. See if we have understood the idea. I like PIQs. يكسر رتابة lecture. Okay. So let's give it about 2 minutes. A particle moves from x equals 0 to x1 due to a conservative force along the x-axis. The force has the same maximum magnitude F1 in all three situations shown. Rank the situations according to the change in the associated potential energy during the particle's motion, most positive first. Remember, change in potential energy is in the opposite direction of the work done. Okay. Ahmed, what do you see? I can see that you are connected, but what do you see when you're trying to see the question? Just reloading. Why? I had other people in the other section also complaining of the same. Okay, do something. If you are on a computer or on a phone, you can do this thing. If you're on Firefox, open a new private window. If you are in Chrome, open an incognito window. And if you are on your mobile phone, then there should also be some sort of, if you're on iPhone, it's called private mode in Safari. If you are on Android, it's the same thing on Chrome, incognito, or whatever. And try opening it from there. Or are you using the app, the Moodle app? We need to figure out what's going on. It seems to be a problem with a few students. So we have a clear winner, which is number 2, 3, 1, 2. Now let's see whether that is correct or not. It is correct, but how and why? So we need to find the change in potential energy. And we determine that the change in potential energy is equal to minus the work. Now, since we have force and this, the area is equal to the work. So work here is less than 0, negative. Work here is more than 0. Work here is more than 0. Yeah? Now, since we are looking at the opposite side, this means delta U here will be positive. Delta U here will be negative. Delta U here will be negative. Since we want most positive first, this is first. This is smaller than that. 1 is smaller than 2. So this is less negative. This is more negative. The correct answer is 3, 1, 2. Good. So gravitational potential energy. Say I have an apple here down on Earth, okay, ground level, and I'm taking it up to some point YF. What is the change in my potential energy? Well, potential energy change is minus the work. My force is mg, minus mg. My d is dy because I'm working in the y-axis. From initial position to final position, doing the calculation ends me with mg delta y, or mg delta the distance. So I call it mgh, actually. So h for the distance, the height, whatever it is. Okay. But here's the question. If I say my gravitational potential energy is mg y final minus y initial, how do I determine what is y final and what is y initial? Is y initial 0? So here we said y initial is 0. Is y initial always 0?
No.
No.
No. Can I make it always 0?
Maybe.
Turns out, yes and no. The answer is maybe. So gravitational potential energy of an object depends on what we call, on its position, respect to a chosen reference level. So we compare everything with that level. We choose a level, we call it level 0, and then we end up going up. Okay. Has anyone here ever gone to North America? So the US or Canada.
Yes.
Okay. Have you also been to anywhere in Europe? Or actually, never mind, in Oman. You are in Oman. لما تدخلون البيت أي طابق هذا؟
ground.
Ground floor?
First.
floor.
أول.
Ah. See, this is very interesting. Some people are saying this is the ground floor. Some people are saying this is the first floor. من فيكم صح من فيكم غلط؟
Both are correct.
Okay. Salim has another option. He says this is floor 0. Okay.
No one's wrong.
Turns out it is all reference frame. It's all relative. If you call الطابق اللي تدخلون منه الطابق الأرضي معناته الطابق اللي فوقه هو الطابق الأول. إذا تسمون الطابق اللي ندخل البيت منه الطابق الأول معناته الطابق اللي فوقه هو طابق رقم 2. طيب في ناس عندهم بيسمنت في البيت يسمون البيسمنت ليفل 0 معناته you have 0 1 2 أو you have -1 0 1. You have many options. In North America, they usually call the floor you enter from the first floor. So في كندا وفي أمريكا يسمونه first floor. في بريطانيا وفي أوروبا وفي آسيا بشكل عام نسميه ground floor. فالبناية في عمان وفي آسيا بالعادة إذا هذه نفس البناية في آسيا زائد أوروبا this is ground 1 2 3 4. In the US, this is 1, 2, 3, 4, 5. And this is exactly what we do here. Now, my reference level is initially here. Okay, this is my 0 level. U2 is more than U1. صح? That's obvious. U2 is more than U1. I can move my reference level to here. Look, it was here. I moved it here. Now the potential energy of the object at my reference level is 0 because I changed my reference level. Yeah? Okay. What if I take it even further up? So it used to be here, then here, then here. What if I take it further up? Now it's weird. Now this potential energy is positive, but this potential energy is negative. طيب ما هو قبل شوية كان 0. It's just because I chose a stupid reference level this time. So how do I choose a reference level? How do I choose a reference level? Well, if I choose my reference level to be on, let's consider a book on a table that is 1 meter high, and then I take it 2 meter high above that. On the table, my potential energy is mgh, h is 1, so mg1, صح? What about all the way up there in the air? What's its potential energy? Is it mg2?
MG3.
It's mg3. Good. I decide to change my reference. من هنا أجي هنا. Now what is my reference level على الأرض?
Table.
mg -1. والكتاب صار 0 mg0 وفوق صار mg2. Okay. Now, what is important is not what the potential energy is, but the change in the potential energy. When I had my reference on the ground level here, Final was mg3, initial was mg1, the difference was mg2. When my reference is at the table, final is mg2, initial is mg0, the change is still 2mg. So the change remains the same. And that is the important bit. Anyone confused about this? Okay. What about elastic potential energy? Well, I start from here. I stretch it all the way there. My force is minus kx. And I'm telling you that elastic potential energy is conservative. W by spring is independent of the path taken. It's only dependent on the initial and the final positions. What is the work of elastic, we said? Half kx squared. Final minus initial, half kxf squared minus half kxi squared. That's elastic work. No, there's a mistake here. There's a big mistake here. It should be this. So the work, we said, is initial minus final. And the potential energy change is minus that, final minus initial. When I am at the happy position, at the equilibrium position, my x is 0. So my elastic potential energy is simply 0. So if I am comparing to the ground level, my gravitational potential energy is mgh. If I'm comparing to the equilibrium level, my elastic potential energy is half kx squared. Yeah, someone was saying something? No? Okay. Okay. Now I am going to go to the whiteboard, okay, because I don't really like the way your book goes about this thing and confuses the crap out of me. I have an object that is falling down from here to here. What are the different energies that are associated with this system or with this movement? Tell me.
What again, doctor?
So I have an object عندي كرة جالسة تطيح من أعلى البيت، هذا بيت، إنزين، الكرة جالسة تطيح من أعلى البيت إلى أسفل البيت. What are the different types of energies associated with this?
Kinetic energy. And,
okay, we have kinetic energy to do with movement, half mv squared. بعد
Gravity.
okay, gravitational. What kind of energy is gravitational? Gravitational
potential energy.
So mgh. بعد
Drag force.
drag force. حلو. بعد لما الكرة توصل على الأرض تنفعص شوية صح؟ وبعدين ترجع عدلة مرة ثانية. elastic Maybe. You have different types of energies. صح?
Frictional.
Okay. Friction, so drag force is a type of friction, yes. Now, say, for example, think about a little child. Okay. Your little brother, your little sister. You bought him or her a set of Lego blocks. Lego, مكعبات. Now the box, when you opened it, okay, has 1,000 blocks. No, has, let's make it easy. It has 10 blocks. Okay, مع الأطفال صغار. في 10 مكعبات. Now you open the box in the room. You close the windows. You close the doors. Okay, the blocks are in the room. تجي بعد ساعة تلاقي there are only 7 blocks. What is the first thing that comes to your mind?
They jumped from the window.
But the window is locked. The window is locked. It's not open. You check. It's still locked. It's not open. Okay. Rayan seems to have experience. Eat it. That's one option. It might be, you know, the kid has ate it. The kid hid it under the mattress, put it in a cupboard, hidden somewhere, right? But what is the thing that you are absolutely sure of?
The blocks in the room.
The number of the blocks is 10. If I cannot find it, it means it is hidden somewhere, so I need to find it. صح? This is energy. Energy, okay, there is a rule, okay. Now there are some tiny exceptions later on in very, very advanced physics, but as far as we are concerned at this level, okay, and I'm sure you have learned this in school, okay, we said that energy cannot be created or destroyed. It can only be changed or transferred from one form to another. Yes? Do you remember learning this at some point in life?
Yes.
Yes.
Okay. Now, based on this, if you enter the room and you find 13 blocks instead of 10 blocks, what does this mean? You opened the bag. There were 10 blocks in it. Now suddenly, there are 13 blocks in the room. What does this mean? Anyone?
Maybe it doubled.
Yeah, but how? Remember, we're not talking about very weird stuff happening. We're talking about everyday things.
Maybe extra old stuff.
Maybe extra old stock. Maybe your brother or sister's friend came to play with them and forgot 3 of their blocks with them, right? But these 3 blocks need to be accounted for. We cannot just have extra 3 blocks, or just blocks cannot just disappear, right? Now, this is exactly the same with energy. the total amount of energy in a system, if we say the system is isolated, okay, what do I mean by isolated? I mean, I define a range of object and I define this as my system. It's not interacting with anything else in the universe. كذاك وحدهم وحيدين فريدين مساكين كذاك وحدهم صوب من العالم. Now, if that happens, the amount of energy there is constant and they can move around, صح؟ الكينيتيك ممكن يعطي الجرافيتيشنال ممكن يعطي الالاستيك ممكن مثلا يرجع للكينيتيك. مع الحركه you have drag force, you have friction maybe, you lose the energy to thermal energy. So drag force takes you, for example, to something like thermal energy مثلا، او مثلا what's it called? Thermal energy, internal energy. Yes? But the total of these needs to remain sum of energies needs to remain constant. صح?
Yes.
Okay. So we come back to the example of our ball. الحين, this starts here with initial velocity 0, and هنا it has some final velocity, some number, which means that kinetic energy here was 0 and kinetic energy here is some number. صح؟ صح؟
Yes.
اوكي. الحين نسأل السؤال اللي لازم الكل يشتغل عليه في المستقبل وفي الحياة، انزين، عشان نتخلص من الفساد في هذا البلد. من أين لك هذا؟ Where did you get this kinetic energy from? كان عندك صفر قبل ما تستوي المسؤول الفلاني. من وين لك العمارتين هذول؟ من وين لك الكينيتيك انرجي هذه؟ من وين جاؤوا؟
From potential energy.
Good. Which means if this is 0 and this is number, it needs to come from somewhere. Probably from gravitational potential energy was some number here. And if we take the gravitation here, this to be the 0 level, reference level. So this is here. Okay. So we had gravitational potential at the top. وإحنا نازلين, we are losing gravitational potential and gaining kinetic energy. And at the end of the day, we end up with the energy transfer from somewhere to somewhere else. But overall, the amount of energy is constant. هل الفكرة وضحت؟ حد عنده أسئلة على الفكرة حتى الآن؟ Okay. So we accounted for the kinetic energy. Unlike البنايات اللي تطلع في عمان والأراضي اللي تطلع في عمان, they come out of nowhere. They don't need a source of funds. They just ينمون من الأرض مثل النباتات. وأنا شكلي مشتهي دال. So, okay, all right. Back to the book. Okay. Now, what we just said on that whiteboard is what 8.2, 8.4, and 8.5 in the book is. But I don't like switching it into multiple sections, so I do them one go. So 8.2 in your book says conservation of mechanical energy. Your mechanical energy is the total of your kinetic and your potential energy. We assume that the system is isolated, which means there is no external force from an object outside the system. Okay? Then this is me with دلة الشاي على satellite. Nothing else is affecting us. Okay? as soon as there is an external force تبدأ تصير مشاكل, because there's force, so they can mess about with the energy. But assuming كالعادة this poor guy كذاك وحده جالس يصحح أوراق كذاك في أمان الله, ما حد يعبره, زين, no external force, no change in total energy. If you have change in kinetic energy, where did it come from? From work. If you have change in potential energy, where did it come from? From work. طيب إذا هذا من work وهذا من work, if you have change in kinetic energy, where did it come from? From potential energy. If you have a change in potential energy, where did it come from? From kinetic energy. المحصلة, the sum of your energy before and after is the same. Okay, the sum is constant. Now I will switch to a different slide وبعدين راح أرجع هنا مرة ثانية. Okay, so this is not the same level as in the book, so I'm skipping to 8.4 and then I'll come back to 8.3. Sorry, just a second. Okay. Now, لما كنا نتكلم قبل شوية قلنا إيش؟ The system is isolated, صحيح؟ قلنا the system is isolated, so the total energy is constant. قلنا potential, قلنا kinetic. طيب what if there is an external force؟ تعرفوا الناس حشريين, حتى لو أنت شايل معك كوب الشاي ورايح آخر الدنيا على ساتلايت في الفضاء الخارجي تشرب, بعد بيجي لك واحد أقول إيش تسوي؟ Okay, so external forces will come. Now, what happens if an external force provides positive work? If it provides positive work, it's giving extra energy, صح? So your energy content in your system will increase. طيب, but we know most people don't do this. Most people مزعجين وبيجي وينكد عليك ذاك الكوب مال الشاي بيخليك تلعن اليوم اللي سويت فيه الكوب. Negative people, they take energy away from you. Okay, they take energy away from you. الشاي بيبرد وانت ما استانست فيه وسحب منك الطاقة الحلوة اللي كانت عندك. Negative work, they take away your energy. Okay, so نرجع. طيب, so far we have not spoken about friction. Work is equal to the change in mechanical energy. This is what your book is saying, okay? بعد كل هذا برجع للوايت بورد وبتشوفوا انه الكتاب معقد السالفه وهي بسيطه شويه. اوكي، قبل شويه وش قلنا؟ دلتا كي بلس دلتا يو از ايكوال تو 0. conservation of mechanical energy في 8.2. في 8.4 جينا نغير، قلنا دلتا كي بلس دلتا يو از ايكوال تو دبليو. ايه زين، تعال دخل فيها فريكشن. فريكشن فورس ولا ما فورس؟ فورس ولا ما فورس؟
Force.
فورس ولا مشي فورس يا متعلمين يا بتوع المدارس؟ Please tell me you know عيال كبرت. I will feel very very bad if you don't. Okay, it's a force. As a force, it does work, which means إنجليزي ده يا مرسي. You have thermal energy. One more type of energy. I will skip all of this. آخر شيء. إنزين. The law of conservation of energy. Total energy of a system, which includes all the types of energies: mechanical, thermal, internal, potential, kinetic. Okay, in a system is constant if there is no external force. If there is an external force, depending on what that force المزعج يسوي, if it's a nice guy giving you energy, positive, إنسان كذاك positive في الحياة, إنزين, it will give you extra energy. If it's negative, كوب الشاي مالك بيبرد, you will lose energy. Okay. Wait, what's happening here? Wait. Stop. Okay. So, to conclude, المفيد من الهلمة دي كلها. In an isolated system, in an absolutely isolated system, we cannot have an external energy transfer. So the total energy of an isolated system cannot change. So you take the total energy of a system and it's constant, otherwise known as, so I can write this rule in two ways: E mech plus E thermal plus E internal equals constant. So sum of the energies constant, sum of the changes zero, لأنه overall the change is zero. It's an isolated system. Now I go back to this. Remember this? What we did here? Now, if this is an isolated system, what is the total change of energy in it? أنا عاوز جملة مفيدة. Good. Okay. If it's an isolated system, the energy is constant and the change is zero. If it's not an isolated system, if it has a work being done, or if it has an external force,
Not constant. There's
okay,
change.
then it's not constant. There's a change, and that change equals to the work done. So far, so good. Any questions about conservation of forces? Sorry, conservation of energies. No? Okay. I would like to show you something, and then we can do a couple of PIs, and then we're done for the day. Okay. Here's a pendulum, and we will learn about the pendulum later, okay? But it's basically hanging in the air. I want you to look at the left part here, where it says KE, PE, thermal E, and total E. Okay. Now, look what happens when I'm taking it, when it's here down, ما في شيء, صح? As I am taking it up, so of course what I'm saying at the moment is, is that هنا وين مكتوب واحد, this is my zero level, my reference frame. As I am taking it up, ايش يصير? My potential energy increases because I have gravitational potential, صح? Now when I leave it, what will happen? What will happen to the energy when I leave it?
It will transfer to kinetic energy.
It will transfer to kinetic energy. See, you can see, I'll make it slow, and you can see on the left, potential energy decreases, kinetic energy increases. When kinetic energy is maximum, potential is zero, and vice versa. And your total energy is fixed. Yes?
Yes.
This is assuming no friction, no drag. What will happen when I start putting drag in? When I put friction in, what will happen?
The total
The
energy.
total energy will decrease until it comes to zero.
Look what happens. My thermal energy is increasing, so I'm losing energy to heat. And what's happening to my kinetic energy and potential energy? They are still switching, but now they are competing with the thermal energy because they're losing out. Now you will notice the total energy has not changed, but the percentage is changing. You see the red percentage of thermal is increasing, and the amount available for kinetic and potential to play with is becoming less and less all the time. Now, to make this faster, I will increase the friction. Okay. And you will notice something. You keep going. You keep going. And then eventually, you see the movement is much, much less because you have lost a lot of energy to heat. And then eventually, what happens is your entire energy that you started with went to thermal energy and it stops moving. That's it. Okay. So what happened here? Initially, there was no energy. Then I gave it energy by using an external force. The external force was my hand lifting it. So this is an external force doing work, positive work, giving it energy. And then the change was, and then the system is isolated. So the change in energy is zero, but it's just flipping between different types until we run out. Cool? And this is the same with masses and on a spring. Yeah, look, zero energy. Here I have kinetic energy for movement, potential energy for gravity because it's going up and down, potential energy for elastic because there's a spring, and I have thermal. Yeah, and I'll start with no damping. This is my 0 point. This is my equilibrium 0 point. I stretch it. Look, I'm stretching it. And the more I am stretching it, the more elastic potential energy I have. Stop. Yeah, or if I'm compressing it, look, more elastic and more potential gravity because I'm not taking it higher. And then it's just switching between elastic, gravitational, kinetic. And then when I introduce thermal, eventually it just stops. But you will notice something weird. This time, unlike the pendulum, in the pendulum, we ended up with zero kinetic, zero potential, and full thermal. But here, we have half thermal, little bit of elastic, and little bit of gravity. Thermal did not take the whole thing because this thing is still in the air, so it still has gravitational potential. So thermal took all it can take. It cannot take any more, and that's it. We're stuck at this configuration. Okay, so 120, we'll stop here. Next lecture, we will start with doing these 3 PIQs, which are very, very fun. And then we will continue with 8.3, which is more mathematical and a little bit less fun. Okay. Do you have any questions on what we did today?